Let's apply our general method for this particular module to solve some of the problems where we will have to solve for the velocity and acceleration for a system of rigid bodies. So I'm going to start with a 4-bar linkage system. So let's say we have this as the 4-bar, right? Why is it a 4-bar? Because ground is first link, this is second, this is third, this is fourth, okay? So in this 4-bar linkage system, there are only 3 rigid bodies that are moving, okay? We have 2, we have 3, we have 4. So the first thing we have to do is identify the choice of quadrant frame, reference frame that we are going to use in this case. And for now, we just focus on the translating frames. So we'll have just a translating frame and I can show it anywhere I want. Let's call this point O2, this point O4, this point A and B, and that's X and Y axis, okay? All right, so X-axis is pointing to the right, Y-axis is pointing up, okay? And we have the length of the linkage system given to us. So let's say this is L2, this is L3, this is L4. We also know that initially the angle this is making from X-axis, let's say that's theta 2. We can say we also know the angle that this is making from X-axis theta 3, and we also know the angle this is making from X-axis, let's say theta 4, right? So this is the linkage configuration at particular instant. Next instant there will be a different configuration. The lengths will be same, but the orientation of the links may not be same, right? So in this chapter, most of the time when we are doing analysis, we are doing what we call instantaneous kinematic analysis. So we are actually asking the questions like, what are the angular velocity, what are the linear velocity at this particular instant, okay? Because the next instant, the velocity values may change, okay? So this is a linkage system, which is basically what we call a single degree of freedom linkage system. Even though every single rigid body has 3 degrees of freedom, when you join them in a certain way, in this case, this is how they're joined, their degree of freedom actually reduces. Okay, so the link AB and this particular instant doesn't really have 3 degrees of freedom because it has been joined by 2 links on the side. So it has only 1 degree of freedom. What does that mean? It means that you only need one actuator to drive this linkage system, and that actuator could be a single DC motor attached at point O2 that will move this mechanism. So as O2A rotates, the position and orientation of AB and BO4 will be completely known to you. All right, so let's say we know the angular velocity of my input link. Let's say we'll call it omega 2, right? So omega 2 is the angular velocity of O2A. So omega 2 is given to you as some omega 2, all right? And that's since counterclockwise, so we'll write it as k hat, right? So I'm not going to bother writing the numbers right now. We'll just do everything through the symbols, okay? So the step 1 was identify the reference frame. Then step 2 was to show the reference frame. The step 3 is to identify the common points on the rigid bodies, right? So what are the common points over here? So let's write them common points. We have O2 as a common point, which is common to link 1 and link 2. So this is common to 1-2. We have A as a common point, which is common to link 2 and 3. We have point B, which is common to 3 and 4. And we have O4 as a common point, which is common to 4 and 1, right? Those are the 4 common points over here. Point O2 and O4 are trivial points because they're fixed points, so we know their velocity and acceleration will be 0. But point A and B are interesting to us because the point A and B are going to be moving, so we can write their velocities from the perspective of different rigid bodies, right? So that's what we'll do. So let's start with O2A and we'll focus on point A. So the first thing we'll do is we will write the velocity of A from the perspective of rigid body number 2, okay? So velocity of A, choosing O2 as a reference point, which is 0, is omega 2 k hat cross R of A with respect to O2, okay? So this is omega 2 k hat, and what is R of A with respect to O2? Is this vector. So that's L2 cosine theta 2 I hat plus sine theta 2 j hat, and that is omega 2 L2 cosine theta 2 j hat minus sine theta 2 I hat, right? That's the velocity of A from the perspective of rigid body 2. So let's write that as equation 1, okay? So maybe I can write this as rigid body number 2. So on rigid body number 2, we have related the velocity of point A with velocity of point O2, right? In fact, those are the only 2 points of interest on rigid body 2. There is no other point, right? Okay. Then A is also on rigid body number 3. So we'll write the velocity of A for rigid body number 3. So we'll pick rigid body number 3. And for that, we will write again velocity of A. But this time, now on 3, we have the only other point we know something about is the point B, velocity of which is not known to us, but it's okay. We'll just go ahead and write that for now. Velocity of B plus angular velocity of 3, which we don't know. So we will say this is omega 3. We also don't know the angular velocity of O4B, so we'll call it omega 4. Okay, and the objective may be that omega 2 is given to you, and omega 3 and omega 4 have to be found out, right? So if omega 3 and omega 4 have to be found out, those are the two unknowns, which means we will need two scalar equations, and two scalar equations can be obtained from one vector equation in xy plane. So as long as we can write at least one vector equation involving omega 3 and omega 4, we know that we can solve the problem, right? So our objective for this question is really just to get one vector equation, an equation where we have a left-hand side and we have a right-hand side, and some of the terms involve omega 3 and omega 4. Okay, so coming back to rigid body number 3, velocity of A in between is velocity of B plus omega 3 k hat, which is an unknown, cross r of A with respect to B, right? So velocity of B is not known. Let's just go ahead and write that. Omega 3 k hat. What is r of A with this B? It is this vector, right? So this angle is theta 3, so this angle will be theta 3. So this will be equal to L3 cosine theta 3 I hat minus and minus sine theta 3 j hat. Okay, so this is equal to VB minus omega 3 L3 cosine theta 3, or let me just put plus here, and this is cosine theta k cross I is j, so that's minus j hat, and this becomes sine theta 3 I hat, because k cross j is negative I hat, right? So we get velocity of A written like this, and this is, let's say we'll call it equation number 2. All right, so we have equation 1, we have equation 2. Both of them are expressions of velocity of point A. And of course, velocity of point A, whether you see it from the perspective of rigid body number 2 or rigid body number 3, has to be same, right? Because point A is not separating from the two rigid body as this whole thing moves, right? These are velocities as measured in a fixed reference frame, right? With respect to a stationary observer, right? Because that observer is not moving. So these velocities have to be same, which means we can write 1 equal to 2. We can write 1 equal to 2. So if we do that, what do we get? We get omega 2 L2. You know what? Let me not do that right now, but let's just keep in mind that we can equate these two equations, right? The reason I'm not going to write these two right now is because we do know omega 2, we don't know omega 3, but we don't know anything about VB, right? So let's see what we can do about VB. Now B is common to 3 and 4, right? B is common to 3 and 4. So we can write the velocity B from the perspective of 4. Okay, from the perspective of rigid body number 4. Now we're not going to write the velocity of B choosing A as reference point for number 3, because that equation would be basically same as this. Okay, we have already related the velocity of A with velocity of B. So there's no point in now writing velocity of B choosing A, because you'll get the same equation. Okay, so now let's write velocity of B equal to velocity of O4, which is 0, plus omega, this is omega 4, right? This is omega 4 k hat cross r of B with respect to O4. So that is equal to omega 4 k hat cross L4. So let's write this position vector. Is this as cosine theta 4 I hat plus sine theta 4 j hat, and that is equal to omega 4 times L4 cosine theta 4 k cross I is j hat minus sine theta 4 I hat, right? So that's the velocity of B. Now we can take this velocity of B, let's call it equation number 3, and substitute in here in 2. Okay, so if we do this, then on the right hand side of equation 2, we will have omega 3 as an unknown, and we will also have omega 4, right? Now we can equate 1 and 2. Okay, so this is what we will do now. All right, let's do that. So first let me write 1 from here. So that's omega 2 L2 cosine theta 2 j hat minus sine theta 2 I hat, that is equal to VB. So let's write first this. Okay, so that's omega 4 L4 cosine theta 4 j hat minus sine theta 4 I hat, and then we'll write this last term, which is plus omega 3 L3 minus cosine theta 3 j hat plus sine theta 3 I hat. Now this has become a long expression primarily because I'm refusing to substitute numbers here. I'm just writing everything in terms of symbols. In fact, this is useful because if, let's say, somebody said, hey, why don't you write a MATLAB program to compute all the angular velocities with time, then actually you would need to do this kind of derivation in terms of variables and symbols so that you can program them, right? If you substitute numbers over here, then it won't lead to a program. All right, so this is what we get. This is one equation, right? This is an equation where we have, on the left hand side we have I hat and j hat. On the right hand side we have coefficients of I hat and j hat. All we need to do is combine them together, right? And then we can write two equations. So let's do that. So I hat, coefficients of I hat on the left hand side are minus omega 2 L2 sine theta 2 equal to minus omega 4 L4 sine theta 4 plus omega 3 L3 sine theta 3. That's, let's say, equation X. And then for the Y component, j hat coefficients, we have plus omega 2 L2 cosine theta 2 equal to omega 4 L4 cosine theta 4 minus omega 3 L3 cosine theta 3, and that's equation Y. Now we have two equations and we have two unknowns. We have omega 4 as an unknown, omega 3 as an unknown. We can solve for both of them, right? So what this is telling you is that if you have a problem like this and you have, let's say, one of the inputs given to you and the question is asking for two outputs, right, which in this case are angular velocity of 3 and 4, then you will need to generate at least one vector equation, okay? Now, it doesn't matter what is given to you as an input. In this, if you look at this x and y equation, I don't care which of these three numbers are given to us, omega 2, omega 3, and omega 4. Okay, I could be given omega 2 and I could solve for omega 3 and omega 4. I could be given omega 3, I could solve for the other two angular velocities, and so on, right? Because this is just an equation involving all these variables. How would you do the acceleration analysis? In the same way, okay? So you identify the common points and then you would write the acceleration of point A. So you will write the acceleration of point A, and then you would write the acceleration of point B, and then you would substitute for the acceleration of B in the expression for acceleration of B, something like this, and then you'll be able to solve for angular velocities. Now, whenever you have to do acceleration analysis, you always have to do velocity analysis, okay? You cannot really do the acceleration analysis without completing the velocity analysis. Let's do another example where we have a slider crank mechanism and we want to do the kinematic analysis of rigid bodies in slider crank mechanism. Now, we've seen in a slider crank mechanism, we have a crank and we have a slider, okay? And this slider is constrained to slide along this fixed line, which is shown to be horizontal line over here. So as the slider moves back and forth, the crank is allowed to rotate in a certain direction, right? So this kind of mechanism you see in an internal combustion engine where the input comes from the piston side, piston does to and fro motion and the crank rotates, and the crank is in turn connected with the wheels of your car or the truck through a transmission system, and that's what makes your vehicle go actually, right? But this kind of mechanism can also be used in the other way. So if let's say you wanted to generate a straight line motion, okay, and from a, let's say a DC motor, you could connect your DC motor right over here to the crank, okay, and as the crank rotated, the piston would move back and forth, right? So you could use this mechanism in the other way as well. So given a circular motion, rotary motion, how do you get a linear motion out of that, as opposed to what you do with the mechanism employed in internal combustion engine, where the input motion is the piston's motion and the output is the crank connected to the wheels. Okay, so let's say, we have this mechanism and we know the angular velocity, right? So I'm going to pick actually a particular configuration just to make my life a little bit, easier when computing this, all right? So I'm going to make my crank to be completely vertical at this instant, and that's my connecting rod, and that's my piston, all right? So this is O2, this is point A, and we'll call this point to be P. Again, let's count the number of rigid bodies we have. We have one ground, we have the crank, we have the connecting rod 3, and we have the piston. So this is also a 4-bar mechanism. So 4-bar mechanisms are very, very popular. In fact, I would say 95% of mechanisms out there used in machineries are actually 4-bar mechanisms, okay? So we saw one kind of 4-bar in the previous example where all the links were connected via revolute or the hinges. And over here we have, some revolute joints or hinges. This is a hinge joint, this is a hinge joint, this is a hinge joint. But then we also have this sliding joint, right? This is a piston that slides on this horizontal surface. And that's essentially a sliding joint. So let's say we know the velocity of the piston, okay? So let's say this is going this way and the piston is moving this way, and we know the velocity of the piston as Vs, or maybe I should just call it Vp to indicate this is the velocity of the piston P. All right, and the question is, what is the angular velocity of O2A? What is the angular velocity of AP, and so on? All right. Okay, so we're looking for angular velocity of 3. Let's call it omega 3. We are looking for angular velocity of O2A. Let's call that omega 2, right? And since we don't know whether they're going to be moving clockwise or counterclockwise direction, although in this case you can clearly tell that O2A has to move in the counterclockwise direction if the piston P is moving towards left, right? Okay, so we will just assume it to be counterclockwise direction and we will solve for them, right? So what is the process? The process is to identify the coordinate frame, translating frame. Let's show it. Okay, so that's my X and this is my Y, right? So Y is pointing same direction as O2A because O2A is vertical. Identify the common points. So what are the common points? Common points. O2, which is common to 1 and 2. We have common points A between 2 and 3, P between 3 and 4, right? Okay, that's it. So those are the common points. Now O2 is a trivial point, it's a fixed point, right? So let's write velocity of A choosing O2 as a reference point for rigid body 2, right? So velocity of A choosing O2 as a reference point, which is 0, omega 2 k hat cross R of A with respect to O2, which is omega 2 k hat cross, let's say this length is L2, right? So that's L2 j hat, and that is omega 2 k cross j, which is minus I hat, right? That makes sense because we know the point A is going to be moving a circular path with respect to O2. Since O2A is going towards the left, A has to be pointing that way, right? That initial direction to that circular path, and that's why negative sign. Right? Okay, we can also write velocity of point A with respect to rigid body 3, choosing P as a reference point. So let's do that. Velocity of A choosing velocity of P as a reference point plus omega 3 k hat cross. We need to write this vector, right? L3. So we need to know something about this angle. Let's say this is theta. So that's L3 cosine theta minus I hat plus sine theta j hat. Actually, I'm writing theta 3 here. So let's find, let's just do theta 3. That's okay. So what about velocity of P? What do we know? Velocity of P is given to you. That's negative I hat. That's great. So minus Vp I hat plus omega 3 L3 minus cosine theta 3 k cross I is j. This is sine theta 3 k cross j is I hat, and that's negative, right? So, you can see that fortunately we don't have to do any more derivatives and integration from now onward. Not that many, of course, but mostly it is vector algebra we are doing. So you need to be able to do these cross products very, very quickly because you'll be doing quite a few of those. Okay. All right, so this is one equation, this is second equation. Both of them are expressions for velocity of A, right? And they have to be same. They can't be any different. So let's equate them. So what do we have? We have minus omega 2 L2 I hat equal to minus VP I hat minus plus omega 3 L3 minus cosine theta 3 J hat minus sine theta 3 I hat, right? Okay, so let's equate the coefficients on the left and right hand side. We have minus omega 2 L2 equal to minus VP minus omega 3 L3 sine theta 3. Let's call that equation X. And then 0 equal to, there's no component of J hat on the left hand side, minus omega 3 L3 cosine theta 3. And that's equation Y. Okay, all right. So L3 is not 0, cosine theta 3 is not 0. That means omega 3 is 0. So at this particular instant, remember you're doing instantaneous kinematic analysis. At this particular instant, the angular velocity of the conducting rod is 0. Okay, that means that it is not rotating at this particular instant. It is going to be rotating, maybe next instant was rotating at the instant before, but at this particular instant at least it is not rotating, right? Okay, all right. So omega 3 is 0, which means we substitute that here. This becomes 0, and that gives us omega 2 equal to Vp over L2. Okay, so this kind of makes sense actually. So what happens in this case is when O2A is vertical, the piston P is actually at its extreme left. Okay, it's at extreme left, which means that momentarily PA stops rotating. Now at the next instant it will begin to rotate, but at this particular instant it has to stop rotating. All right. Okay, so that's the basic analysis for the velocity, right? Now if I wanted to do the same analysis for the acceleration, I could do that. All I would have to do is, after I finish doing the velocity analysis, I would do the acceleration analysis. The reason I always have to do velocity analysis, even if the question is only asking for acceleration, is because I will need to know these omegas. And you will recall in the expressions for acceleration, you have terms like omega cross r, right? And those terms you won't be able to write unless you have the angular velocity. So let me write that down, in red color, that always do velocity analysis before doing acceleration analysis. Okay, because you will need angular velocities.